Here's the first question of AP Physics 2024. We can see it's about photoelectric effect experiment. Let me read the question problem statement for you quickly. In each trial of photoelectric experiment, a scientist used a device to shine light of a single frequency on two different metals, 1 and 2. The device can emit light with frequency FA, FB, or FC. Each frequency of light is used to test both metals. The scientist determines the minimum de Broglie wavelength of the electrons ejected from the metal in each trial of the experiment. The following table summarizes the results of the experiment. For each trial, the scientists analyze only the electrons with the minimum de Broglie wavelength. Here we can see the table. Alright, 3 different frequencies, A, FA, FP, and FC were used. They were exposed on metal 1 and 2, and we can see sometimes electrons were ejected, and sometimes, particularly in the trials numbers 3 and 4, no electrons were ejected. Alright, here comes the first question. In a coherent paragraph length response, indicate which frequency, FA, FP, or FC is greatest and which frequency is least. Justify your answer using physics principles. Good. Now, before we start analyzing the table, let's quickly recap about the photoelectric effect. Now, the photoelectric effect states that when a light is exposed, when a light strikes a metallic surface, it is possible, not always, but it is possible to eject electron from it. But it depends on several factors. First, the energy of the coming light, coming photon. The energy can be also expressed as Planck's constant times frequency. Now, the energy of the light should be at least equal to the so-called work function of the metal. Now, work function is, as analogy, I say it is the price that needs to be paid to the metal to take electron from it. So, logically, the energy of the light should have at least work function energy to take electron from it. If it is less, no electrons would be ejected. If it is more, it is possible to transfer the extra energy to the electron in the form of kinetic energy. And the maximum kinetic energy that the ejected electron can have is equal to, logically, energy of the photon coming minus the work function. All right. Now let's compare the frequencies. Now we can see that the frequency is directly related to the energy. That means if you have higher energy, higher frequency, less energy, less frequency. Good. Now, let's start with the least frequency because it's easy to see from the table. We can see that frequency B, trials 3 and 4, when this light was exposed on the metals, no electrons were ejected. That means energy of frequency of light B was the smallest. It was not enough to overcome the barrier. So let's start from there. Energy of a light is directly proportional to the frequency. We can add the equation here. Energy is equal to Planck's constant times frequency. All right. Since light with frequency B could not eject electrons in both metal 1 and 2, it must have the least energy. Therefore, FB is the smallest. Okay, this was easy part. Now, we have to compare what is left, A and C. Now, to do that, let's choose trial number 1, when FA was exposed on metal 1, and trial 5, when FC was exposed on the same metal. And we can see, and we can compare the Broglie wavelength, and we can see that when FC was exposed on metal 1, de Broglie wavelength was smaller. So how can we use this information to compare frequencies? Here, we must remember the de Broglie wavelength equation, which is equal to Planck's constant h over momentum, which can be written as Planck's constant divided by mass times velocity. So we can see that de Broglie wavelength is inversely proportional to the speed. So if we are having smaller de Broglie wavelength, Fc is resulting in smaller de Broglie wavelength, it means that the speed of the electron would be higher. And if you remember, kinetic energy is related to the speed square of the speed. Kinetic energy is equal to half mv square. That means more speed, more kinetic energy. So here, logically, we can see that Fc is resulting in higher kinetic energy. So when we can say when the lights with Fa and Fc were exposed on the metal one, Fc resulted in lower minimum de Broglie wavelength. Now, speed is inversely related to the de Broglie wavelength. Let's shorten it. Thus, Fc is resulting in higher speed, since K max is related to speed square. Fc is resulting in higher K max too. What does this mean? Initially, the energy of light C was higher. As a result, we are talking about same metal one. That means work function is same, but we are resulting in higher kinetic, maximum kinetic energy with Fc. That means initial energy was higher. That means the frequency was higher. So let's summarize. Then comes Fa, and the smallest one is Fb. All right, next question. Calculate the maximum kinetic energy of the electrons ejected from metal 1 in trial 1. Assume that the momentum P of an ejected electron can be described by the classic definition is equal to mass times speed. Okay, let's start. Actually, we wrote it above, but let's write it one more time here. Is equal to P. De Broglie wavelength is equal to H over mv. From here, we can rewrite the equation for speed, which is equal to Planck's constant divided by mass times wavelength. So since kinetic energy is half mv squared, let's bring this into this equation. So kinetic energy becomes half h squared divided by m wavelength squared. Next, substituting numbers. So we have half Planck's constant from the formula sheet. You can see it is equal to 6.63 times 10 to the power of negative 34 joule times second to the square. And mass of the electron can be also found from the formula sheet, which is equal to 9.1 times 10 to the power of negative 31 kilogram times. Now, from the table, we can see in the trial one, the wavelength is given as 6.9 times 10 to the power of negative 10. So 6.9 times 10 to the power of negative 10 meter square. Now, the rest is the calculator's job. I already did it, and it's equal to 5 times 10 to the power of negative 19 joules. All right, which you can convert to electron volt. You should divide by 1.6 times 10 to the power of 19, which gives you approximately 3.13 electron volt. Okay, done. Part C. Indicate whether the work function of metal 1 is greater than, less than, or equal to the work function of metal 2. Justify your answer by referring to the table of results. Now we have to compare work function of metals. To do that, we have to choose some trials. 3 and 4 is not useful here because no electrons were ejected. So we have to choose somewhere 1 and 2 or 3, 5 and 6. Let's choose 1 and 2 because we are having the same frequency, Fa, but we are having different metals and we are having different de Broglie wavelength. Now, if you look, we can see on metal 1, when Fa only was exposed, we are having on metal 1 smaller de Broglie wavelength. If you remember, earlier we talked that smaller de Broglie wavelength means higher speed, means higher kinetic, maximum kinetic energy. All right. So, the Kmax is related to 1 over de Broglie wavelength square. When the light with Fa was exposed on both metals, in metal 1, electrons did have smaller de Broglie wavelengths and higher maximum kinetic energy. Now, since work function is equal to energy of the light minus maximum kinetic energy, metal 1 has a lower work function. Because it's having a lower work function, it is letting electrons ejected having more kinetic energy. All right, this is the end of the first question.